All right, welcome back to this video. So as we were doing for the other algorithms in the other video, we're going to do the same thing for XGBoost here. All right, so we're going to start by importing this XGBoost. So from XGBoost, we're going to import XGBoost as SGB. All right, just shorten it so that we're not be writing XGBoost over and over again. All right, so I'm going to shorten XGBoost as SGB here. All right, now from XGBoost.scaling, I'm going to import SGB regressor. All right, this is what we're going to use to build the model, and then as we did for the others, we're going to initialize it over here. All right, after initializing it, then we fit it. All right, we fit it just like we make it lane. Okay, just like we make it lane. All right, then after running it, everything is working fine for us. All right, it's some warnings here which we can actually get rid of it, right? Removing the future version, blah 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 blah. So they just keep on giving you some warnings that is going to be removed. All right, so after that, after building our model here, all right, after building the model over here, we can actually use it to make some predictions and store these predictions in what is called the YPred, right, to make predictions and store it here. Okay, so now we can check the performance of our XGBoost, right, after initializing it and then fitting it, making it lane. Right, we can actually perform the score and check how well it is doing. All right, so if we do that, we can see that it's making 94% on the training data. All right, on the training data, it's making 94%. Not that bad, but maybe you could have done better than that, but not that bad as compared to the support vector regressor that we dealt with in the other video. All right, so over here we can also check the score on the testing data, and it's making 88%. A bit closer as compared to the others. This is a bit closer, right? 88 and 94 is a bit closer as compared to the other algorithms that we've been dealing with. Not that best, but it's a bit closer than the others. All right, so over here we can do the same thing. I mean, it's just going to give us the same thing. We're going to use this to add to add this accuracy to the data frame, the accuracy data frame that I've created. All right, so here we can check the error and then see the error is 30. All right, I think this is the lowest. The other ones we're having was, the lowest that we've been having so far was the 31. All right, and this is the 30. So this is the lowest error that we've been having, and the highest closest the highest gap, which is between the training and the testing. Right, so this algorithm is doing quite well. All right, so we can add this also to the data frame that we've been building. All right, so XGBoost, we can add the accuracy there. All right, and then after that we can also move on to decision tree. Right, we can move on to decision tree. So as we did for the others, we first initialize it and then we fit it. All right, then we fit it. Okay, after that, after we run and everything is fine, we can actually check which features are very important and which features are not important. All right, so we can actually check. We have different features. All right, we have the age, we have if we go up and then see our data set that we've been dealing with over here. Right, over here we go one more step up. Yeah, over here we have different features. We have cement, slag, ash, water, super plastic, coarse, aggregate, fine aggregate, age. Which of these features are important, which are not important, which are contributing, which are helping us to actually predict the strength, all right, of this concrete, which features are helping us to predict this concrete. So we can check all those features that are important, right, and those that are not important. That's what we call the feature importance. So we're going to see which features are doing well and which features are not actually contributing to this. Okay, so with this, for you just using the feature, our model that we did here, right, we created the model to be DEC underscore model, right, for the decision tree. All right, then we can use that one dot feature importance, then we can get the feature importance. After that, we are putting everything in a data frame, right? We are putting everything in a data frame, and then the column of the data frame, we are calling it importance. So let me just show you how it's actually going to look like. All right. So we have the feature importance, like just this letters that we wrote over here. All right. And then after that, we put everything in a data frame, and then we name that column as importance. All right. We name that column as importance here over here. All right. The columns that we want over the index, we are seeing that is supposed to be the column names that we have in the X train, which is the same as the column names that we have in our DF data set, right? So the cement, the importance of the cement is 0.3. The importance of the slag is 0.05, which is very less. The importance of ash 0.007. So ash is not actually contributing to for us to know if the concrete is how, I mean, for us to determine the strength of the concrete, right? So the ash is not actually contributing for us to know the strength of the concrete. The same way, I mean, water is contributing here, right? Is a bit higher, 0.12 is a bit higher. Super plastic is not contributing much. Coarse aggregate is not contributing much. Fine aggregate is not contributing. Age is contributing very well for us to determine the strength of the concrete. All right, so the important features here are age, water, cement. All right, so cement, water, and then age, right? These are the features which are important and which are helping us to determine the strength of the cement. All right, so we can actually okay, let's before we actually select the important features and use that one to determine the strength of the strength of the concrete. Let's perform some predictions. All right, so we don't forget we created this DEC underscore model, all right, over here for decision tree. Yeah, we created this DEC underscore model, right? That's our model. So we're going to use that one to make some predictions, and then after that we will store it over here, right, in what is called y underscore pred. So this one is going to override all the y underscore pred that we've been doing earlier on. All right. So after that, we can check the score. This score is coming from the training, right? I think this is the highest score that is coming out, 99% on the training data. So let's see it on the testing data and see 77. All right, now you can see the gap, 99, 77. All right, it's supposed to, I mean, if it is 90, it's okay. I mean, 95 or something like that, or 90, 92, something like that, but not even 80, but 77. All right, so this model is actually overfitting. All right, it's performing very, very well on the training, but very, very poor on the testing. All right, so this one is just going to give us the same thing, so that we'll be able to actually add this score. All right, so the error, let's check the error here, 57. All right, 57, which is very high. All right, so let's add this accuracy. Let's add it to what we've been already having over here. All right, so decision tree 77, we've been able to add it over here, and then after that we can actually perform a k-fold cross validation on that. All right, so the same thing that we've been doing here. So in this case, we are going to run it 18 times and then find the mean of all these accuracies that we've been getting. All right, find the mean of that, and then we are going to add this one also on the algorithm and the accuracy data frame that we've been creating. All right, so we have the decision tree performance there, and then the k-fold, you can see here k-fold is actually performing better than the decision tree itself. All right, when we perform the cross validation on the decision tree, is actually doing better than the decision tree itself. All right, so after that we can actually we can create a copy of our data so that we will not mess our data up, right? So that we select the features which were helping us to predict the strength of the concrete. All right, so these These ones were not actually contributing. Obviously, we don't want the strength to be part. The strength is actually going to be our dependent variable, so we drop that, or automatically we were going to drop that. And we also found out that ash, coarse aggregate, and then fine aggregate were not actually contributing. If we check the feature importance again, let's go up and then see. All right, ash, very bad. All right, it's not actually contributing. Coarse aggregates and then fine aggregates, they were not contributing, so we're going to drop that. All right, we're going to drop that, and then if they are not helping, we drop them. Okay, and then after that we do our splitting again. Right, x train, x test, y train, y test. We're going to split it again and then perform we're going to scale it. After dropping, we scale it again just like we did up there, right? So we perform this z-score on the x train and then the x test. All right, so that we have a more scaled data to work on. All right, so that no data will outweigh the other or something like that. All right, so we're going to scale it, and then after that we perform the decision tree regressor again. All right, remember the decision tree regressor we're just dealing with. So we initialize it again, and then just like we're doing here. All right, remember initially we started with decision tree over here, going up a bit. Okay, so we have the decision tree over here. Okay, so starting with, we initialize it, all right, then we fit it. So the same thing we're going to do after dropping the features that are not important. We are going to initialize it again. Remember, we have done everything again, just like we started earlier on. So we're starting everything afresh, and then we drop in the features that are not contributing. Okay, we drop in them. Then after that, we fit it again. So we're going to run it, and everything is fine. Okay. Then after that, we check the feature importance again, just like we just did for the other one. All right. We just check the feature importance again. Now over here you can see that cement is actually contributing, slag not contributing much, water, all right, contributing, age is contributing, superplastic is not contributing. Remember, they were not contributing earlier on. We gave them the benefit of the doubt, but still is showing that they are not contributing. So somehow you can actually drop them and then do it again. Okay, so let's make a prediction on this again and then see how it's doing. All right, so if we check how well it is doing on the training data, I mean the data that it has already learned from, is making 99%. Obviously it has already learned from this, it's supposed to do better. So if it's doing 99%, it's not that surprising. All right, however, if we check on the testing data, it's doing 75%. Huge gap. So you can see that this is overfitting. All right, this data is, this model is actually overfitting. It's not helping much. All right, if we actually, this is going to give us the same thing, so that we'll be able to add it, all right, to our algorithm and the accuracy data frame that we have. So we add in this decision tree 2. All right, the decision tree 1 is the one that we did with all the features in there. Then after that, we perform some k-fold on that, and then we remove the features that were not important, and then we did it again. We fitted the algorithm again. All right, so after that, we name it as decision tree 2. All right, so that you not conflict with the decision tree that we already did earlier on. All right, so over here we can drop the strength and then pick all the other data points that are in there. All right, pick all the other data points that are in there, and then scale it again. All right, you can scale it again, and then perform the. So over here, what we are going to do is actually perform some hyperparameter tuning. All right. Previously, we did not check in the maximum the depth of the tree that we are building. We did not do anything, right? So here we're going to do some hyperparameter tuning. We have the right to change these maximum depth of the tree that we want to build. All right, so we're going to consider 4, right, as the maximum depth of the tree. All right, we're going to consider that, and since obviously it's going to be random, all right? And then the minimum sample leaf, the leaf we want it to be 5, all right? So all these are hyperparameters that you can actually tune to get your model to perform better. So we check the feature importance again, just like we did earlier on over here, right? Just like we did earlier on over here. We're going to do the same thing after doing some hyperparameter tuning. We're going to see how these features are. So now this one is making it clear those that are not contributing. So slag obviously was not contributing. Ash, coarse aggregate, right? Fine aggregate, they were not contributing. Right? Superplastic, they were not contributing. But age, cement, water, they were contributing. So they are actually showing obviously very well here. All right. So we're going to actually plot this. We're going to plot this tree, right? And we're going to use graphics. So if you don't have graphics in your Jupyter notebook, you just use this command to do that. I have it, so I'm not going to run it. I'm going to comment it out. But if you don't have it, you can just run it like this. Use this command and then pip install graphics, and then you can get it. All right. Since I have it, I'm not going to run that. All right, I already have that one installed, and we're going to use what is called a pi.2. If you don't have it, you just install it. All right, I've already done that. So if you run this, you just get this requirement already satisfied because I already have it. And then if you run this again, you get requirement already satisfied because I have it already. So I'm going to use this. You're going to from scikit-learn.tree. I'm going to import export graphics, right? So over here you can see that we're going to import what is called the export graphics from scikit-learn in sklearn.tree, all right? And then from also string IO from externals.6, which is present in sklearn, and also image, which is present in ipython.display, and graphics.py. So if you don't have it, you just install it using these commands, right? I pip installed and the package name over there. All right. So we've done that. We're already satisfied. All right. So over here we just this is just a scaled DF that we already scaled previously. All right. So we're going to drop the strength out of that. All right. So if we should go all the way up, you can see that initially when we started this, we scaled our data right over here. Right, so we have a scale, then we apply the the z-score on the x here, right? After that, we put everything into a data frame, and then we called it a scaled df. All right, so within that, we're going to just drop the strength. All right. So let's go all the way down there. Okay. So that's what we're doing here. We're just dropping that and then showing that it is present in the axis or present in the column, all right? And then after that, we have what is called the feature calls, and then we store all the columns in the scaled DF, right? Apart from the strength, we store everything in what is called the feature calls. Now, if we see inside the feature calls, we can see that we have cement, slag, ash, water, superplastic, coarse aggregate, fine aggregate, and then age, right? Without the strength. So all these are just the column names that we have in our data frame, all right? Without the cement, all right? Without the strength, we drop the strength from there. All right, so after that, we will start by building the tree. All right, so let me just zoom out so that you see the tree very well. All right, so it's having some true and then false here, and this is not a factory rule to do that. All right, so we just initialize the string IO, which you're going to use over here. And then, as I said, if you don't have these packages, you just install them. And if you want to know all these parameters that we have here, it's simple as just searching for this export underscore graphics in the documentation. You can see all these hyperparameters that we are using here. This DEC underscore model underscore prune underscore model is nothing but what we did here when we did some hyperparameter tuning by setting the max depth equals 4 and the others the mean sample leaf to be 5, right? We store everything here in what is called the DEC underscore prune underscore model, and that's what we're using over here, right? That's what we're using here. Okay, so these are not it's not any strange hyperparameters that we're using here. With this, just a single search of this in the documentation, you get to know all of these. All right, and the feature names are just the feature column names that we stored over here. All right, that we're putting over there. All right, and then we have the pilot. So if you don't have it, you just install it over there. All right, so I mean, there's no factory rule to do this. You can just search this string IO, and I mean the export graphics. I mean in the documentation, you can easily get to know all these hyperparameters that we have over here. Okay, so this is our tree, and this is the data that we have over here. All right, you have some true and there's some false, right, and some conditions being set over here. I'm quite sure if you're a bit familiar with decision tree, this is no rocket science over here. It's just some conditions set here, age being less than or equal to negative 0.405, and then the mean square error here, the samples that we have, all right, and then the value that we also have here. All right, so it's just checking conditions age. If the age is less than or equal to negative 0.40, and then it will go to if it is true, it go to this part, and if it is false, we continue from this part. All right, the same thing happens to all of the leaves that we have in our tree. All right, so there's no fast rule over here. I mean, if you're not familiar with decision tree, I mean, I just urge you to just search a decision tree and then read it from the documentation. I mean, just take some 2 minutes or 3 minutes out and then just read it. You get to know it. All right, it's not anything difficult to do that. All right, so after that, as we do for all the other algorithms, we'll make some predictions. So we're going to use the same thing. All right, this is the algorithm that we created when we did some hyperparameter tuning up here. All right, when we did the hyperparameter tuning up here. Okay, we created this algorithm, so we're going to use that one to make some predictions down here. All right, going to use that one to make some predictions down here, and then after that we can check the score on the training. All right, on the training, so let's see how it is doing. 75%, which is extremely bad. All right, extremely very bad. If this is the data set that it has already learned from, and if it is making 75%, and then it's very bad. If we check on the testing, we see that testing is getting worse. Obviously, if the performance on the training is getting bad, then performance on the testing is supposed to be very bad. All right, so this is actually going to give us the same thing, and we need it to be able to add it. So the error is supposed to be very high, as I said, 116, which is the highest error that we have recorded so far. Very high. All right, very high. So we can add this accuracy. We can add this accuracy to the accuracy data frame that we have. All right, we can add it. Okay. Then we can also perform some k-fold cross validation as we did for all the other algorithms, right? And it's doing very bad. So obviously decision tree will not help us in this case, right? And then we add it as well. All right, so you can see that is actually the least performance that we have. The k-fold cross validation for decision tree, the pruned one. All right, it's actually the worst that we have so far. Okay, so we can also go back and then do the same thing over and over again by just hyperparameter tuning. I mean, just changing what we did max that equals 4. Probably that's not the ideal. We can also change the max depth and the leaf size, and right, and then build this again. Okay, we can change the hyperparameters that we have over here, and then rebuild everything again. Okay, and then see the performance. All right, so you can run that. You can just come back and then change these hyperparameters in here, and then see how things work. And even with the cross validations that we do for all these algorithms, you can also change the hyperparameters in the cross validation, and then see if your model is going to perform better. All right, so let's go down there and then see the compilation of these algorithms that we've been able to do, and see which one is actually performing better. All right, so let's check all these algorithms that we've been compiling together and then see. All right, so if we can see over here, we can see that if we see individually, we can see the random forest is having 87%, gradient boost regressor 88%, and then we can also see for bargain regressor 86. XGBoost is actually doing good considering the X train and the Y train performance is actually doing better. So we can actually choose these 3 or 4 algorithms and then drop the rest, and then we can go back and hyper tune. All right, check the hyperparameters in there and then change these hyperparameters to make sure that these algorithms are performing better, and then finally choose one out of them. All right, so this is how we're going to actually do it finally, to actually go back and then choose different hyperparameters for these algorithms, and then see how well they are going to actually perform. All right, so you can drop all the rest and then go back and then take the same process that we just did and then change the various hyperparameters, change them, and then see how they are going to work. So you drop everything and then maybe you pick random forest, you pick bargain regressor, and then of course you pick XGBoost. All right, and then you forget about the rest. Okay, and then you do the cross validation, you do the hyperparameter tuning for all of them, and then finally you come back to see which one is also performing better than the other, and then you choose that one as a final model. All right, so that's how you're supposed to actually do it. So let me leave that for you. You can just go back and take the same process that we've been doing, right? Just hyper tuning it again and then changing the hyperparameters in it. All right, so let's end the class here. Let's end the this project here. We will meet in the next project. All right, so keep practicing, keep learning. Have a nice day. See you in the next project.